Okay, so in this video we're going to take a look at the number e. Alright, so another one of math's famous constants, not as famous as pi. Pi being, I guess, probably the most famous math constant here. But let's take a look at the number e and what that has to do with exponentials and just continuous, or the compound interest formula that we had that we looked at earlier in this module. Right, so the compound interest formula, right, was something like this. Okay, let's see if I got that right. Second guessing myself here. Yeah, I think that's right. Okay. All right. NT, no R. Yeah. Okay. Okay. All right. So that is our compound interest formula. Okay. And here we're going to take a look at really this quantity here, where R equals to T. We just set it equal to 1. Right? And we want to focus on this value, right? And really what it comes down to is how often we compound the interest. Right? We went over monthly, once a year, daily, but what if we just did it every second, right? Every waking moment? What would that look like? All right, so in other words, we would like to see here what happens, the limit as that n goes to infinity, right, of this quantity. Okay, and here we'll just kind of do it by just kind of plugging in numbers and seeing what happens, right? So I'm gonna switch over here to my, I have a window of Desmos open here. So, right, and one thing that we notice here, as n gets really large, this goes to 0, and that's going to infinity, right? So really, what this is kind of trying to represent is this, right? But I do not know what that is, right? This is something that's called an indeterminate form, where is 1, we define 1 to any power to be 1, right? But is 1 to infinity 1? Right? Infinity is not really a number, right? It's more like a concept, right? So how do we exactly deal with this? Right now, in the calculus course, you'll go over a way to evaluate a limit like this more analytically. But here we're just going to take a look at really large values of n and see if it converges to anything. All right. But at this point here, I don't know what this is. I can't say that it's 1, but I can't really say that it's anything else. I need to do a little more investigating. All right, so let me switch over here to my Desmos. Okay, so what we have here is, as you see here, I have that equation. Instead of x, I swapped out x for n for x, I should say. All right, and what we have here is a table of values, and right here I have the first 5. Now it does look like it's converging to something. In other words, it has like an asymptotic type behavior. I'm going to hold off this idea of convergence, right, for a more calculus, for a calculus course, right? But here, let's see what happens when I make the values larger, right? Let's say what happens when x is 100. Okay. All right, so now notice here we started off with 1, it was 2. 2, it jumped to 2.25. And then from 2, when we get to 5, it's at 2.48. Right, but to 100, it looks like it's slowing its growth, right? It looks like, okay, well, how about 1,000? All right, 2.71. Okay, so let's see, how about 10,000? All right, so now 2.7181. All right, and if I add another 0, it looks, and I'll increase it by powers of 10. Right now at 100,000, it still looks like 2.7182. Let's add another 0 here. And it looks like I think we've reached kind of an approximate value here that I don't think it's going to change much more, right? Even if I add another 0, it looks like I'm not gaining much, right? I'm increasing at each time by 10 times as many values that I had previously, right? From 1,000 to 10,000 to 100,000, right? So an order of magnitude 10 times as much as the previous one. Okay, so it looks like it's approaching this value here. Now, if you don't recognize it, I mean, I don't blame you. Like I said, E is not as famous as its its other math famous constant as pi. But let's take a look now. What is this value here? So I'm going to switch back over here. Okay, and I have a TI 83 plus. And your TIs, it's probably located in the same kind of area here. If you look at here in the yellow, in the top left corner of the division sign, we see that letter E. Right? That is the constant. You notice right below pi. So if you do E, oh, now look at that, right? 2.71828, and I believe that's kind of what we were settling on. E is an irrational number, right? So it kind of keeps going forever with no discernible, no pattern. Right? So if you look here, what was it looking like we were getting? 2.71828, 1, and then I got an 8 here, and this has a 7. So pretty close to what we have here, right? So it turns out what this, hold on a second, let me get back to where I was here. So as it turns out here, that this is equivalent to the number E. All right, and the way you can evaluate E raised to any power, right, you can use, so the calculator also has this E to the X one right above the natural log. Right, so we can do second E to the X, and you can raise it to any power you like, 5. All right, or you could raise it to the power of pi if you want. Okay, so you have a nice shortcut here of E to raise to some power, but you can also just use the number E itself and then use the caret parentheses 2. It gets the same idea, right? But we know how to raise it to a power when needed, and it is going to come in handy because actually, as it turns out, all right, if we take the limit as n goes to infinity of this whole thing, right, actually what this, remember, n is the only one that is getting taken to infinity. The rest of these are fixed, right? R and T, they're fixed values, P, so they're not competing with n, right? N is the only one that goes to infinity. So this actually converges to this. Right? And what we actually have here is not the compound interest formula, but what we have is what's called the continuous growth formula. Continuous, and usually when we're dealing with money or any kind of business application, we call it the continuous compounding formula. All right, where P, again, same as before, is the initial value, R is the interest rate per unit time, usually yearly, and T is the period or term of investment, and again, usually yearly as well. All right, now in general, right, when we're not dealing with any kind of financial applications, we just use, and here this is amount at time t, right? The amount is a function of time. And in general, when it's not any kind of financial application, we use this continuous growth or decay. All right. The growth or decay would depend on the rate. If we're talking about decay, R would be negative, and growth, R would be positive, and then A is our initial amount, same as before. Okay, so that is how we arrive at this number E, right? Which kind of it arrives from that compound interest formula, right, which I think is rather interesting here. Let's take a look at an example where we apply this formula. Right, so how about here? Let's say a person invests $100,000 at a nominal 12% interest per year. Now this is a crazy high amount for interest per year. Right? Compounded continuously, what would be the value of the investment in 30 years? Okay. All right, so compounded continuously, so it's telling me what formula to use. All right, so this is continuous, compounded continuously, the formula for that. So our principal, what we started off with, is 100,000. Our rate, remember, E is a fixed, E is a constant, so E is the number E. The rate is 12% per year, so we'll take T to be in years, and we want to figure out what happens at the end of 30 years. Okay, so A of 30 is going to be 100K, 100,000. E, R is 0.12, T is 30. Okay, so we got our calculator here, and again, be careful we're using this. So 100,000 times E, and in the exponent, 0.2 times 30. You want to be very careful, right? Mine opens up the set of parentheses when I hit the caret here, but make sure you have the parentheses around this whole quantity. Okay, 0.12 times 30, and then hit enter. And here we have, after 30 years in this account, our 100K would turn into $3,659,823.44. Okay, all right, not a bad deal, right? Again, and this is assuming that you're not making any additional investments, right? Now, this formula really is not modeling, but essentially a more realistic type of thing. I mean, we might have 100K that we have to just kind of store away and not think about, but most likely what we would do is we put away each month a certain amount, right? And then that will continually earn interest, right? And in that case, we would use a different kind of formula, but for here, this works out for this type of problem. Okay.